Okay. Can you hear me? Can you
Yes,
see the
sir. You
desktop?
can.
Yep.
Yes, you can see.
Okay, great. Um, okay. So let's see. Try to. Okay. So first, I got the videos from last week up on the YouTube finally. So if you want to see last week's videos, they're up there. What we talk about today, I'll put that here. There'll be a link to today's video up here after class sometime this evening. Okay. And okay. What I want to do today is go back to the fork join and do another example. Remember, last week we looked at, let's see, okay, I downloaded the fork join code. It's in this folder here, okay? And we were doing these examples that came from this one kind of online book, okay? So we were doing the examples that come from here, okay? And we were doing this, what amounts to this chapter 3. Okay, so we were doing the examples from this chapter 3. And we noticed that we didn't get any speed ups. Yeah, the real problem, I mean, the idea was really good. I mean, what this book shows is a good idea, but we got absolutely no speed up when we did these examples. Okay, so we can do it again. Okay, so like here's one of the examples. This is the example that uses fork join. If we compile it and run it, let's see. Oh, that was this. Now let's see. I forgot. That was a small. That was a. Let's see. Increase the size of the problem. Okay, and what? Wait a minute. Oh my goodness. We're back to the parent. This is not the version we were working with last week. The server is acting really strange. This is back to being only the parallel version. The serial version is missing from here.
Oh, I didn't have a serial version either for that download. I just had to code my own.
And I put it up there. It's up there. Something's going wrong with the web server. If you have a problem, let me know. But I put it. I've downloaded it before, and then somehow it disappears, and it's back to this old version. Huh. This is happening intermittently. Somehow, sometimes it's downloading an old version. Sometimes it's downloading the current version. I'm trying to think what I could do to get it up there correctly. I deleted it from this. I deleted the file from the server, uploaded it to the server, and the server still serves a stale version of the file. Okay. Let me check something. See, it's showing a version from over a week ago. It's showing a really old version, and I've uploaded it since then. Okay, now let me get the more recent version. It's on my computer. see, this one's serving a zip file that's 314 kilobytes. It should be just a little bit bigger than that. Should be a little bit bigger than that. Let's see. No. Okay, so here's the from my hard drive. Here's the example we were looking at. Okay, and there's the parallel and the serial version. Okay, it's there. Boy, anybody have a clue what could cause a web server to keep serving up an old version of a file?
Not a clue. I've never had any of my servers do that before.
Yeah, I know that you can get caching at different levels if you're using sometimes what's called content content. I forget what they call them, but you to speed up web access, you can have caches at different places. Okay, content delivery networks. That's what they call them. CDN, content delivery networks. You can be using a content delivery network, and then you can have caches. That's usually used by big companies like Amazon. They'll have caches all over the country. I don't think Purdue Cal has got caches all over the country. I don't even think it has caches all over Northwest Indiana. So I don't know how that could. Yeah. Okay.
Have you restarted the server, or do you even have access to
No,
do
I
that?
don't. Yeah, I can only upload things to the server. Boy, I wonder if the server's got some sort of built-in cache that's kind of screwed up. I don't even know what server software they're running on the server. I've never checked to see
Apache.
if they're. Is it Apache?
Yeah, it
Yeah.
said so at the bottom of the web page.
Oh, I forgot about that. Yeah, it probably says that.
Some version of Apache.
Yep, right. Yeah, it's some version of Apache. Right. Okay. So, yeah, I'm sure Apache probably has some kind of caching built into it. Maybe it's gotten mucked up. Okay. I wonder if I just give it a new name. I bet what I should do is put it up there with a brand new name. And then it can't cache it. Yeah, that's what I'll do. I'll put it up there tonight. I'll put this zip file up there, this fork, and I'll just call it fork join 2. Yeah, I'll put a new link. I'll rename the file, upload it, and create a new link with a new name, and I'll bet you can download it then. Okay. So now, if we compiled it, well, let's see. Let me increase the problem size to something medium size. Okay. Okay. Remember, the big problem was that the fork join time, which is using all 12 cores, is hardly different than the serial time, which uses 1 core. And like Andrew said, I'm pretty sure Andrew's right that this is just, we're bottlenecked by how fast we can read memory. Because all we're trying to do is, this example from this book is trying to sum an array, and there's just a limit to how fast you can read an array. So I've got another example to show you that now I realize that it's probably just bottlenecked on memory. The question is, like, what would be some other example we could use in fork join? And here's a famous example here called the Fibonacci numbers. And it's a really dumb calculation, but it does speed up properly. Okay, so the Fibonacci problem is compute the Fibonacci of n is equal to the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Okay, so it's sort of like a bit like factorial. Okay, it's a, yeah, the Fibonacci of the nth number is the sum of the Fibonacci of the 2 Fibonacci numbers below it. Okay, if you think about this, this is a tree. the Fibonacci of n needs to compute two numbers. The Fibonacci of n minus 1 and the Fibonacci of n minus 2. But each one of those needs to do their own recursion, okay? So you end up with two more branches down here. You end up with a branch down here and a branch here and a branch over here and a branch over here, okay? This one's going to compute the Fibonacci of n minus 2 and n minus 3. This one's going to compute n minus 3 and n minus 4, okay? Now, if you do this calculation in a dumb way, which is what we're actually going to do, you're building an exponentially growing tree of calculations. So, for example, if you want to compute the Fibonacci value of, say, I mean, this is in the algorithms textbook. They talk about this example a lot. Like, the Fibonacci of, this one recursion causes two recursions. Those two recursions cause 4 recursive function calls. Then the next layer will be 8 function calls, okay? So this will cause, like Fibonacci 100 causes a massive number of function calls, okay? Like if this was, okay, so the number of function calls grows exponentially, okay? So this is usually used as a test case. It's just a way to stress your computer. Compute the nth Fibonacci number and do it recursively like this, just as a way to make your computer do a massive number of calculations. Okay. Now, you can make this into a fork join program. So this is the initial job put into the fork join queue. Then this job splits into two tasks, which are put into the fork join queue. Well, this one will branch down into this one, and it'll put this one into the work queue. Another worker thread will steal this one out of the work queue, and it will break this task into two tasks, put this task in the work queue, and go into this task. Just like we talked about last week, that the way the work stealing works is each task is split into two subtasks recursively. This thread goes into that task. This thread puts that task in its work queue. At the beginning, that'll get stolen by another worker. If later on, it won't get stolen, but at the beginning, this will get stolen. And then this task will be broken up into two tasks. And then it'll go into this task, and it'll put this in its work queue. This will be broken up into two tasks, be a task down here, something else in the work queue. Okay. And you'll get a massively big work queue. Okay. Here's the code for it. Okay. Here's a Fibonacci task. Okay. It's going to compute the Fibonacci of a number. Okay. When it's done, the number will be sitting in this field here. This field will hold the number. There's a method to get the answer. Okay. And then here's the compute method. If you're below a threshold, okay, then you just compute the number sequentially. Okay. Which does the recursion, what the sequential version here just does this recursion, but all on one thread. So the sequential version does this recursion just on one thread. Okay. If you're not small, you create two Fibonacci tasks, one for the left half and one for the right half. Okay. So that would be one for here and one for here. You create two Fibonacci tasks. You fork one of the tasks. That puts it in the work queue, and then you just go ahead and jump into the other task. So that was the idea, that when this guy creates these two tasks, this thread puts one of the tasks in the work queue, and it jumps into the other task. Okay, so it puts one task in the work queue, jumps into the other task. When it returns, that task has been completed, but then it has to join on the one that went into the work queue. Okay, when both those tasks are finally done, you just add them up, and that's the answer. Okay, so there's the there's computing Fibonacci. Now, in the example we did the other day that didn't really work, the tasks were cut an array in half. Sum up the left half of the array, sum up the right half of the array. The trouble with that was you had to read the array, and reading the array is what the bottleneck was. In this example, there's going to be no bottleneck on memory. This is absolutely, completely, 100% CPU bound. It doesn't even need to read memory, because it's when you finally get to the sequential version, all you're doing is making these function calls. You're just making tons of little recursive function calls. So it's really CPU bound. There is no big data array to read out of memory in this case. Okay. Here's the sequential version. The sequential version ends the recursion at n equals 1. For example, up here, I told you what Fibonacci is, but the Fibonacci, you have to have something that ends the recursion. The Fibonacci of 1 is, the Fibonacci of 1 is 1. Okay, so that ends the recursion. Okay, so over here, if the, actually, and also the Fibonacci of 0 is 1. So those are the two stopping conditions. So here, if you get to n less than 1, so if n is 1 or 0, actually, I'm sorry, if Fibonacci of, I'm sorry, it's Fibonacci of 1 is 1 and Fibonacci of 0 is 0. Okay, so if n is 1 or 0, if n is 1, you return 1. If n is 0, you return 0. Okay, those are that's the stopping condition for the recursion. Otherwise, you add up Fibonacci of n minus 1 and Fibonacci of n minus 2. So there's the actual recursive Fibonacci calculation. Okay, here's the fork join version of it, and here's the fork join tasks. Here's the actual recursive function calls. Okay, then here is a threaded version of Fibonacci. Okay, that says you compare this one to the fork join version. This one is, these were fork join tasks. Okay, these are fork join tasks. This is threads. So what this does is it says that if my numbers, if the input number is below the threshold, I do it sequentially. If the input number is above the threshold, I create 2 threads, not 2 tasks, 2 threads. Start one of the threads, run one of the threads. So start a thread, run a thread. Then when this thing returns, that job is done, but you have to wait for the forked thread to finish. Okay. So what this one does is it creates a thread. This thread creates this thread over here, then this thread goes down into here. This thread creates a thread for over here, then this thread goes down into here. This thread, whenever it runs, will create a thread for over here, then this thread will go down into here. So it's creating not a thread for every branch of this tree, but a thread for every other branch of the tree. So you create a thread for this right half, but then this thread goes down into here. Then this thread creates a thread for this half and doesn't create and then goes down into here. This thread creates a thread. So if whatever the size of the tree is, there's as many threads as half the size of the tree. Okay. This is absurdly slow. even though it's running in parallel, this, we'll see in a minute, this is absurdly slow because we saw this last week too when we did this with the other one. It completely overwhelms the operating system with millions of threads. If you try to compute the Fibonacci of 100, it'll literally try to create millions of threads. So it totally overwhelms the operating system. Okay, then down here, we're gonna run them. Let's see, I wanna reorder this. I wanna run the fastest one first. The fastest is gonna be the fork join. The second fastest is actually the single threaded version. The single threaded version is gonna be slower than fork join. And then the slowest version is gonna be the multi-threaded one. The multi-threaded one, even though in theory it should be as fast as fork join because they're both using threads, because fork join is so clever about only having as many threads as there are cores, but having lots of tasks. And this one creates as many threads as this one creates tasks. But this one only has as many threads as there are cores. So this one and this one both create a gazillion objects, but this one creates one thread per object. This one creates one task per object. Yeah, Andrew?
Why doesn't the operating system have a feature like this to handle thread pools?
Probably they just don't think it's a part of the job of the operating system. They probably, there's all this thing about what should be in the library and what should be in your language and what should be in your operating system. My guess is that if you bake this into the operating systems are hard to update, hard to maintain, hard to tweak. If you put it in a language library, that's a lot less work to update. Okay, so my guess is this: the operating system, you could, Microsoft could just say, "Hey, we're going to put fork join we're going to make it a part of the operating system." But operating systems are hard to update, hard to patch, and people would just say, "Why bother?" Just have it in. C++ has it in its library now. Java has it in its library. Python has it in its library. And then what can you do? Then you could tweak it for the C++ library. You could, the Java version could be tweaked for the Java library. There probably is no, here's another point of view. The operating system itself never needs this. The operating system wouldn't be fork joining calls to the hard drive. So you can make the case that the operating system itself would never need this. So
I'm more for the point that this is scheduling. We are scheduling the running of specific tasks, which is what we use the operating system for.
No, that's this case down here. But this case down here, no. Well, this case up here, we're doing our own scheduling in the work stealing way, and we don't want the operating system to do the scheduling. Okay, now, since we're doing the scheduling ourselves up here by work stealing, it doesn't really matter if we do it or the operating system does it. It's going to be the exact same thing. There's only a small number of threads, and there's a huge number of tasks, and the threads pull tasks, they're not scheduled. The tasks aren't scheduled on the threads. The threads just go and pull tasks out of the work queue. So there's not a scheduling issue at that point. Okay? The operating system schedules the threads, but there's only a small number of them, and then the threads just pull job tasks out of the work queues. That's not a scheduling problem. I mean, that could be part of the operating system, but then the operating system wouldn't be scheduling anyway. Like this computer has 12 cores, so that means that this is going to run on 12 threads. The actual scheduling of those 12 threads is done by the operating system, but the operating system is going to be smart enough to slap one thread per core, so it's not even going to be interesting scheduling. The whole point is to keep the number of threads equal to the number of cores. And then the threads themselves, they just have this big data structure called a work queue, and the operating system doesn't care what the threads are doing. The fact that they're pulling tasks out of a data structure is immaterial to the operating system because it's not a scheduling issue. So there's really no benefit that I can imagine that of putting this into the operating system itself. Okay, the operating system schedules threads, and what we're doing now is we're just telling our threads, you have this big data structure to read out of. Every time you're finished with a little bit of work, go back to your data structure and get a little bit more work to do. Okay, so it's not really thread scheduling. This one down here is thread scheduling, because this one just very naively and dumbly creates millions of threads and just expects the operating system to schedule them, and they can't. The operating system can't schedule them well. Okay, let's go ahead and run this one, and we'll see that this one scales. This one scales unlike the one that was working with a massive array. This one will scale. It still doesn't, well, okay, let me show you how it works. Okay, so this program expects the number that it's supposed to compute the Fibonacci of on the command line. So you go down here to the main method, it's looking for a command line argument of what to compute the Fibonacci of. Okay, so when I run the program, see, it's going to complain saying you need to give me a command line argument. So what I'm going to do is I'm going to tell TextPad that when it runs the Java program to prompt me for a parameter. Okay, so now if I run the program, TextPad prompts me for a parameter, I'll compute Fibonacci 20. Doesn't sound like much, but okay. So it took fork join only 2 milliseconds. The sequential version was so fast it didn't even take any time. In this case, notice the sequential was actually faster than fork join. And then the multi-threaded, here's a bit of a hint, the multi-threaded was twice as slow as the fork join. Okay, so that was Fibonacci of 20. Okay, so run it again, go Fibonacci 30. Okay, Fibonacci of 30, fork join and sequential tied. Multi-threaded is 100 times slower, literally 100 times slower, because it created an awful lot of threads. Okay, now let's fork join 30. Now do fork join 40. Okay.
Oh.
Now we're seeing some speed up. Okay. Fork join is 3 times faster than sequential. And at this point, the multi-threaded version is dead. Okay. The multi-threaded version is already choking on the number of threads. Okay. Notice that the multi-threaded version, I'm not sure how long it's going to take. Probably a long time. So right now, my operating system is choking on, actually, I can look it up. Let's see, I go here to details.
It looks like you're spending most of your time in system rather than user land.
Well, I'm already up to 45,000 threads. Yeah, because it's what it's doing in user, it's in kernel mode. Why? See, notice the dark shading is kernel mode. Why is this thing massively stuck in kernel mode?
Because basically all you're doing at this point is creating and starting threads.
Right. We're up to 50,000 of them and growing. Okay. So see, we're up to, we're steadily growing. And yeah, the operating system is absolutely choking on doing nothing but creating threads, creating threads, creating threads, creating threads. Oh, it looked like something died. Okay. Yeah, the operating system just cannot keep, and you can see that it's spending almost like, let's see, the vast majority of its time almost 100%. Well, oh, okay, here. So what is it? About 2/3 of its time is spent in kernel. About 2/3 of the CPU time is spent in kernel. Now, it's not maxing out the CPUs because there's really not much more they can do. They're spending so much of their time in the kernel mode trying to create threads. What are we up to now? We're up to 65,000 threads and growing. Okay, and it's just going to keep growing and growing and growing. Okay, so notice how beautiful fork join is. The fork join thing created just as many objects the fork join version created just as many objects as the threaded version created threads. The fork join version created tasks. The threaded version creates threads. They create equal numbers of them because this code here is exactly the same thing as this code here, except this guy's creating tasks and then shoving them in a work queue. This guy's creating threads and then trying to launch them. Okay, just as many objects are created here as here, but this one is not going to try to create threads. So it ends up being fast as opposed to creating threads being absurd. Now I'm going to have to kill this job okay. Okay. So I kill the job because at this point the threaded version is useless. Okay. So the fork join version, well, okay. Now let me go back to the code. I'll comment out this version is no good. Okay, but we can go and do it. We can run larger versions comparing fork join to serial. Okay, that was what? Well, that was Fibonacci. Was that 30 or 40 we just did?
It's 40.
Pardon me?
It was 40.
40.
That was 40. So now things are growing exponentially. So I'm going to go to, well, I'll try 50. Okay, so let's try 50. It might be already too big. Let's try Fibonacci 50. Oh, now here's interesting. This is the fork join version. Notice that the fork join version very much distributed itself over 12 cores really well. Okay, so the fork join version took about 10 seconds and it distributed itself very nicely over 12 cores. Okay, now we're doing the serial version. Now notice how what's happening with the serial version. It's one thread, but the operating system is moving that thread around the cores. So it looks like all 12 cores are busy, but see, overall CPU utilization is not that high. Well, 42%.
That's because of background tasks.
Probably, yeah. Oh, yeah, it's because I'm doing Zoom. That was a lot of that. Yeah, a lot of the background noise
is like
is
20%.
They're almost 30%. Yeah, so the background noise is nearly 30% on this thing. Okay, now look, the fork join was what? About 6 times faster than the serial. It was running on 12 cores and it was about 5 or 6 times faster. So we finally got scaling. Okay, we finally got remember with the array-based fork join, we got no scaling at all. 12 cores was the exact same speed as 1 core. Okay, so but since this one is absolutely totally CPU bound, we can see the scaling that fork join is supposed to get. The trouble with this example is an idiotic example. You know, computing Fibonacci numbers is not anybody's idea of doing useful work. So it's not a compelling example in terms of, oh, look, I can do something useful on 12 cores. But this is the two examples you see over and over and over again when you read about fork join are the 2 examples we just did. Okay. This Fibonacci example is from the guy who, this is in, if you go look at the book on, remember I told you one of the sources of this is the CLR algorithms textbook. If you look in the chapter in it, it does the Fibonacci example. Okay, so, and then this example's, the other example you see over and over again, summing an array. And the guy who wrote this example, you know, that's this website here. He's actually one of the leading persons in the country on parallel programming. He's at University of Washington in Seattle. He's one of the leading persons. I wish he had come up with a more compelling example, because it wasn't until like last week I realized this is a dumb example, because you get no speed up because you're bound by memory access. So it turns out to be a bad example. On the other hand, the Fibonacci ones, it gets speed up, but it's a totally useless example. I'm still trying to find a good, what's a good example of using fork join? Because I've been looking at example after example, and people do Fibonacci's and max of an array, sum of an array. Those are the low-hanging fruit examples, and you just see them over and over again. Um,
You might be able to do some like basic video transcoding
I was thinking of
algorithm.
image processing. See, yeah,
Yeah.
yeah. I even downloaded. I haven't had time to do it, but I downloaded some huge image files to try to see if that maybe you could do some image processing.
Hmm.
Yeah, yeah. And I bet you can. Yeah, there's probably, or like your example last week, probably doing text processing, doing
Hmm.
searching on large text files. Probably would also be a good example. I
Yeah,
bet.
text searches
Mm-hmm.
are a relatively expensive operation, even on short strings that you can hold in cache, no
Yeah.
problem.
Mm-hmm.
And
Yeah.
you can hold many of them to
Yeah.
feed all of your cores.
The search algorithm is a pretty complicated algorithm. If you go back to your algorithms class and you do there's a dynamic programming version of the string searching algorithm. It's a pretty intense algorithm. It does a lot of work. It has to walk the string, constantly starting at every starting
Hmm.
point, trying to compare the pattern to what's in the string. So yeah,
So, so the algorithm that I was using to do text searching was a lot more complicated than anything we went over in our
the
algorithms
algorithms class.
courses.
Hmm.
I was using grep,
Yeah. Hmm.
which is a
Regular expression
very,
pattern.
very powerful tool.
Yeah, that's a regular expression pattern matching, grep, right?
Yep.
Yeah, so that's a regular expression pattern matching as opposed to the algorithms textbooks usually do a basic simple pattern matching. But yeah, so rewriting these examples in some more, I mean, it'd be nice to either find an example or find the time to rewrite these. But unfortunately, these examples that I find in book after book after book, they're kind of not the most compelling examples around. Let's see, this was Fibonacci, what, 50 over here? And I think if you go to Fibonacci 60, you start hitting problems. It's just going to start taking a very long time to do. Like, don't
Hmm.
even try to do Fibonacci 100. That's already going to be too much. Okay, so this is Fibonacci 6. Notice it distributes itself. The fork join distributes itself very nicely over all 12 cores. Okay, all right. But I think, let's see, it took 10 seconds to do. Oh yeah, this is going to take a long time. You can kind of just let it run in the background, but it's going to take quite a while. Okay.
We could do convolutions on images.
Yes. Yeah. Yeah.
That would
Mm-hmm.
scale easily.
Mm-hmm. Yeah.
The
Some kind of simple.
caching might get tricky.
Yeah. The trouble with the image processing is that it's not going to be simple code like this. Yeah. It's not going to be something that's just like here. Yeah. Here's okay. This code doesn't really change much. This is the code that just says, am I big or am I small? If I'm small, go to the sequential version. That's where the work is going to be. If I'm big, fork. So even if you do a more compelling example, the work is going to be down here. That's the part that's going to be hard to write. If you,
Convolutions aren't
yeah, they're not.
convolutions. While the word means complicated, image convolutions aren't actually complicated,
I know you
which
have
is
to.
amusing.
It, the trickier part is dividing up the data between all the threads. Yeah. So you have to do it. You have to. So it doing a convolution filter over a large image might be a really good example. It might actually end up being a really good example. So like yeah, so that would be the code you put here. See, that would be replacing this or replacing this. What do you do when you get to the bottom? What do you do when you get to a small job? Because when you have a big job, it doesn't matter what you're doing in fork join. This part looks like this. Yeah, for the most part, well, there is a little bit of work here. Here we're taking a big job and cutting it into two smaller jobs. Notice how easy that is here. And it's also easy here. There was cutting a big job into two little jobs. Depending on how you're cutting, like if you're doing image processing, you have to still come up with a clever way to cut a big picture into two smaller pictures. Like you cut it in half, left half, right half, top half, bottom half. Should you cut
Quarter it.
it? Pardon me?
Quarter it.
Or quarter it. But notice that this, you could quarter it. You don't have to do left half, right half. You could quarter it and put 3 jobs into work queue and jump into one of the 4 jobs. So maybe you would quarter it instead of cutting it in half. Okay. There's no reason why you have to cut a big job into 2 little jobs. You could cut a big job into 4 little jobs, and then you would fork 3 jobs, meaning you'd push 3 tasks into the work queue and you'd jump into one of them. Then you would have to join 3 of them, and then you would have to combine. Now, this is the other part that's going to be tricky. Here, these have a very trivial, both this and this had a trivial combine. Just add them. Okay. So then if you try to do a more compelling example here, you might find that the combine step gets to be a little bit like if you do parallel merge sort, this is merging. This is the merge step. So the merge step could end up being, now I think in convolutions, there's no merge step.
In the convolutions for here, you would just add 2 numbers.
No, you would. I don't even know if you do that, because if
you would add 2 numbers, convolutions measure the basically the number of matches,
no, right.
air
but
quotes.
If you did filters, you wouldn't even need to add anything. Because if you filtered the left half and filtered the right half, then you're done. There's really no merge.
Each task would just be writing to a new buffer.
Yes. Yeah. Yeah. So
the complicated part for that would be finding a data type, like an array data type.
Yeah, you have to create it. Right. You'd have to create an image.
Freak out when you're having like 12 things write to it all at once.
Yeah. So the trouble is that I don't know of any really simple example of a fork join. I guess if you want to explain the idea of fork join, these examples are as good as any, because they're simple to understand. They don't do, notice this one's still count, Fibonacci 60 over here, it's going to take forever. This is exponential growth. We're living in an exponential growth world right now. So over here, you're seeing what exponential growth was. You go from Fibonacci 40 to Fibonacci, or let me see, this was it, I can't remember, was this 50 and this one was 60, I think. But we hit a brick wall. You go from 20 to 30 to 40 to 50 and it's scaled pretty well. Then you get to 60 and it's just, you hit a brick wall. That's the world of exponential growth. You go to some point and all of a sudden it's a brick wall. We see that in the newspaper every day now. Okay, and that's what's happening over here. This one's hit the brick at about Fibonacci 60 or so. You hit that, you really hit the big numbers. Okay. Now, let's see. Camera. Yeah, this is another example that works on a huge array, and it's going to hit the same problem. This was computing the sum of squares of an array. And you see these examples in book after book, but they're all going to hit a memory wall. These examples might have been compelling 10 years ago when CPUs weren't with all the different levels of cache and all that. But the way CPUs work now, you just can't write something that accesses memory as fast as possible. It'll be limited by how fast it can access memory. Okay. This one accessed a large memory. These accessed large memory. This one accesses a lot. So all these examples were same thing. This one computed the max of a huge array. This one computed the sum of a huge array, and this one computed the sum of the squares of a vector. Okay, so yeah, you won't get any scaling on a modern computer with any of these examples. Only the Fibonacci one's going to give us any scaling at all. Okay.
Yeah, what I've learned is that Intel, like modern Intel machines, usually will have between 12 and 24 gigabytes a second of main memory bandwidth. And with a 3 to 5 gigahertz processor, just one core on that, you can easily outstrip that if you're asking for large pieces of
Yeah.
data
So
per
even one,
instruction, which you easily can do.
so even one core can saturate the memory bus.
Oh, yes,
One core by itself.
definitely.
So if you,
That's
so
why multi-channel memory is so big in server applications. One channel of memory is 12 gigabytes a second. I've seen machines with 6 to 8 channels of memory for large servers that
Mhm.
you'd find in data centers. And that's generally how they're solving these problems now. Rather than just getting a bigger
Yeah, that would be,
bus, you just make more buses.
yeah, that would be interesting if you ran one of these problems, these memory bound ones on one of those machines to see. Yeah, you would think that they'd have a channel for each core. And if they had a,
That's as far as I know. One core can only access one channel at a time.
Mhm.
So it's not going to speed up your single threaded applications to have
but
more
but
channels of
but one
memory.
but when you fork join it and you have 6 cores and you have six
Oh,
channels into memory,
you will definitely see
yeah,
a giant speed up
yeah,
versus what you can do on your machine.
unless there's some sort of bottleneck at the other end of the channels.
Oh, who the heck knows?
Yeah, yeah. So, because remember, they would all be accessing the same array, so that it could be the same memory at the end of all 6 of the channels, and it may end up being a bottleneck anyway. Yeah. So yeah, it'd be interesting to try it if we had one of those machines, but we don't have one of those machines.
I can rent one if you'd
No,
like.
don't.
Just rent like an hour on one. It'd
Nah,
be a
don't
couple
bother.
dollars.
Yeah. Well, I mean, if you want to try it, you can go ahead. Yeah, maybe if you can, if you could try it and you could like gather data and show it, it'd be interesting to look at it.
Hmm.
So if you could, you know, just if you can get printouts, then yeah, it'd be interesting. If it's if it's only a couple dollars, it might be nice. It'll be educational to know if that actually works or not.
Yeah,
Okay.
like the really expensive machines, even like the biggest, baddest ones you can possibly get, are no more than a few dollars an hour.
Actually, to think of it, um, I I I don't know. I actually come to think of it, I probably should try it myself on this guy. I don't know if this would be one of the machines that has that. This is the Rice cluster. I,
64 gigabytes per node. It's got to have more than 2 channels of memory.
yeah, I know. It's yeah. So the nodes are 64 gigabytes of memory. Uh, I think these are the yeah, those are the 10 core CPUs. So each node has two 10 core CPUs for a total of 20 cores and 64 gigabytes of memory. So actually, maybe I'll try to run it on one of these machines. Um, I could try. I mean, they changed this machine recently. I don't know how to use it anymore. They
Hmm.
changed the scheduler that you use for submitting jobs to it. Okay, so I'd have to relearn how to work on this machine because it was just earlier this semester they got rid of the old scheduler and replaced it with a new scheduler. And oh, here it is, PBS to Slurm yeah. So that PBS was the old scheduler. This is the new scheduler. So they switched from an old to a new. So I would have to learn how to schedule a job on this thing. Yeah, that might be. I mean, it might. But there's actually. Do you have an account on this machine? Because you guys can try to request accounts on these machines.
I think I eventually did get an account. I'd have to look back at my emails.
Yeah, students can get an account on this machine here, and you might be able to just compile and run the Java fork join program on one of these nodes. Yeah. and scale it up to 20. And it should scale up to, if it runs on one node, it should scale up to 20 cores. Okay, and it'd be interesting to see if these array-based programs can scale on one of those machines. Oh, maybe I can try that before next week. Okay. Yeah. So maybe with a powerful enough machine, we could see the scaling. Okay. You'd have to, and that assumes, it depends a lot on how good these machines handle. When you have 64 gigabytes of memory, you expect them to have, it would be crazy to have only one channel that would access that huge, have 20 cores, massive number of cores, massive number of memory, and then have a bottleneck being sitting between them. You'd expect if there could be a massive number of cores and a massive amount of memory, there should be some big pipes between the two, not some like the desktop machine, which clearly doesn't. Okay. Okay. And notice that Fibonacci 50 is just, Oh no, it finally finished.
That's a different one.
That's a different
that
one.
was
No,
the
it's still
40
running.
or 50.
Yeah, it's still running. It's, and my CPUs are still, it's still running on all the core. Oh, notice that there's no kernel time to speak of here.
Yeah.
That little bit of kernel time probably has to do with keeping track of some stuff with Zoom, but the fork join framework is very clean. We're working with absolutely 100% CPU bound tasks, these Fibonacci tasks. So we see if we switch this to one, you see, the kernel time's running at probably 1 or 2% overall. Okay. We're using 100% CPU utilization. Kernel time is negligible. The fork join framework is very efficient. The fork join framework is running entirely in user space. The whole work stealing, work queue idea, which is one of the goals of it. One of the whole points of fork join is that all of the overhead, there should be no overhead and kernel time. There should be no need for, and Andrew, you asked, why not make this part of the operating system? Part of the answer is right here. It doesn't use the operating system. See,
operating system stuff generally tends to be pretty slow. Might as well have a userland application which can deal with it faster.
Because the it's like, look at here. There was probably something, maybe Zoom or something kicked in and something's been kicking in and taking up some kernel time here. Okay, but the fork join framework itself, it's not going to be fork join that's doing this. Okay. All right.
If I remember correctly, processing might handle this well.
Handle what?
Image processing.
Oh,
actually, yes, it will.
Yeah, but
who am I kidding?
Yeah, of course. But writing a fork join image processing thing would be a nice example of something that would be a more interesting fork join than Fibonacci numbers. Okay. That's okay. We've gone through all the examples in this folder, so I've run out of fork join examples. One of the it's kind of messed up. When I did this some years ago, you could play around with these cutoffs and actually see how things would change. You could play around with the cutoff and it would actually, so you could change the cutoff and it would actually have different effects on fork join. But since we're bottlenecking now on memory, it doesn't matter. changing this thing, we can't even play. We've lost the ability to play around and tune the fork join because our bottleneck is, when fork join first came out and I first taught this stuff, memory wasn't the bottleneck. On machines, I don't know, that was like 6 or 7 years ago. It wasn't already, the bottlenecking of memories actually seems to be a fairly, what happened? My machine got very quiet. But I didn't get an answer over here. Oh, this window was paused. When I clicked on, but you can see that the job ended right there. So the job ended right there, and there's the fork joint. And right now it's in the serial version. So right now it's doing the serial version, which is going to take a really long time. But it's one thread now being distributed over all 12 cores. So now the operating system's taking over. There's one thread, and that thread's going to bounce around between all the cores because the operating system just likes to do that. Windows likes to take a thread and move it around a lot. Okay. All right. Yeah, we because of the memory bottleneck, we lost the ability to do. Oh, now let's see the Fibonacci one though. Okay, with this one you probably can play around with this threshold. Okay, so right now the threshold is when you get to Fibonacci 15. So let's try it. Okay, I'm going to kill this one. Okay. Think about it. What does changing the threshold do? When you change the threshold, you're limiting how many of these branches you create. Okay, so you keep forking. In this case, right now, it forks until it like suppose you start with n. Okay, then you get. Oh, notice how one real quick thing about Fibonacci's. See that n minus 2 here and n minus 2 is here. It means you're redundantly computing that value more than once. N minus 3 is here. N minus 3 is here. You're redundantly computing that thing more than once. If you've computed it once over here, why would you bother to compute it again over here? Does that ring a bell? Yeah. Think in the algorithms class. If you computed it once over here, why would you compute it again over here? Have you seen that before?
Yeah.
What's that? You remember what it's called?
I forget, but I keep thinking of left recursion for some reason. That's not what it was.
No, it's called memoization.
Oh yeah, memoization. That's right.
If you compute it once, you cache it, and then you don't bother. And that's exactly this Fibonacci example is exactly when the book talks about memoization, they do this example again. So they use it for fork join, and they also use it for dynamic programming and memoization, because otherwise this n minus 3 is going to be computed over and over and over again. So you can actually speak. The fastest way to compute Fibonacci is using memoization. Fork join is not the fastest way to compute this. The fastest way to compute this is dynamic programming with memoization. Then you can compute really large Fibonacci's. Like we capped out at Fibonacci 60. If you do this with memoization, you can do much larger Fibonacci numbers. Not that it's useful, but you can actually do calculations of much larger Fibonacci numbers if you use the memoization rather than fork join. Okay, now, okay, let's compute. Let's see, Fibonacci 50 wasn't too long. Wasn't that the one that took about 10 seconds?
Yeah.
Okay, yeah, 10 seconds. Okay, now, if I bump this up to 25, now I can't bump it up too much because I'm doing Fibonacci of 50. But if I bump it up to 25, that's well, let's see. Now let's see. That's too much bump it. Let's go from 15 to 20. Okay, so now we'll cut off a lot of the bottom of this tree. So now we'll have fewer tasks, but each task will be bigger. Okay, so we'll bottom out this tree at larger tasks. And the question is, will that speed us up or not? See, it's an interesting idea now. Can we speed it up, or will this speed it up or slow it down? Let's find out. Okay, we're doing Fibonacci. We'll stick with the same Fibonacci number, Fibonacci 50. This had a cutoff of 12, and this one has the cutoff now of 20. And what do we find out? We got about a 10% speed up. Okay, we actually got a little bit of a speed up. So, okay, let's try it. Now, what about the serial one? Well, the serial one is unaffected by the threshold. The threshold was only for the parallel one. So the serial one should give us the exact same. Should take about let's take about 40 seconds. Let's just wait and see. The serial one should be the exact same time. Okay, and over here, next time, let's try a 25 cutoff. Okay, well, yes, notice that the serial time was almost dead set the same amount, okay, for 42 seconds. Okay, now let's try 25 cutoff. Now, at some point, okay, let's see if we get a speed up here. Fibonacci 50. We have fewer tasks, but they're larger ones now. And we still got a little bit of a speed up there, okay? It did improve things. Now, notice that, Andrew, once you asked about tuning these things, given any fork join type job, trying to tune these parameters is not a trivial matter, okay? Because what's going to happen eventually, well, suppose if I keep increasing this threshold, eventually I don't even have any parallelism, because I won't even be, well, let's see. If the threshold gets too large, when you won't have, well, as long as we have at least 12 branches here, we'll have parallelism. So we should actually get speed ups as long as we have 12 branches down here at the bottom. Okay, so again, see, the serial is exactly the same. Okay, so let's see. This was 15, 20, 20. This was 20. This was 25, right? Did we do 25 yet?
Yep.
We did it?
Yep.
So let's try, I don't know, let's go ahead and do 30. So the threshold's 30, which is getting close to the number we're actually computing the Fibonacci of, okay? Okay, so that's a pretty big, okay, compute Fibonacci 50 with a threshold of 30. And we still got a little bit of speed up, probably because we probably still have at least 12 tasks to do, okay? Now let's let's go up to 35. Let this one finish. Notice that we're not getting big major speed ups. We're getting just a little bit faster. There's fewer tasks and they're bigger, so probably there's just a little bit less time spent. The serial time is staying very constant. There's probably, the speed up comes probably just from a little bit less having to go to the work queues. There's fewer trips to the work queues because the work queues are kind of full of bigger jobs now. So let's try 35. Stick with Fibonacci 50. Now we bottomed out. Okay. We didn't get, notice we kind of bottomed out. We didn't get a speed up. We're back to what we were earlier. Okay, so somewhere between 30 and 35 was probably an optimal cutoff of some kind. Okay, so with this example, we can see that with fork join, this is typical of fork join. There are trade-offs between the threshold of when you stop forking. When do you stop forking and switch to the serial version? Depending on the actual algorithm that you're using here, this thing can be very sensitive to that number there. Yeah. Here it's not too sensitive. Let's actually go the other way. Let's try, we started out with a threshold of 15, right? Let's do a threshold of 10. That's going to create a lot more jobs. Okay, that's going to create a lot more small jobs. This may actually cause, I would be surprised if this is going to cause some real performance problems. Because at this point, we might be creating way too many jobs. Let's try it. So this one was 15. Now we're going to go to 10, which is going to create a lot more jobs. Okay, Fibonacci 50. The question now is, how does that compare to this one? I would expect it to be slower. Not by much. Oh, okay. Not by much. Okay. Yeah. It did slow us down, but only about like 10%. Okay. Now the next thing would be go to a cutoff of 5. Okay. A cutoff of 5 is going to really create a lot of jobs because now we're going to fork a lot down till you get to Fibonacci 5. So you're going to be forking till you get down to Fib 5, and then you'll switch to serial. That's going to cause an awful lot of nodes down here at the bottom. So let's see how efficient. This is going to test the efficiency of the fork join system. Okay. Okay. Notice that serial's always going to be the same. So let's go. Okay. Now let's try the Fibonacci 5. Oh, it looks like we're seeing a, see, now it looks like we're seeing a big hit. Yeah, it almost tripled the runtime. When we went from a threshold of 10 to, this was threshold 15, this was threshold 10, this is threshold 5. The runtime really took a big hit now, okay? Because now we're seeing that there's just there's too much, the work queues are growing. We may have even seen, if we go to Task Manager, I think that bump there in memory was the work queues getting really big because we were putting so many little jobs in the work queues. I think that bump in memory was the work queues growing more so than they would have in the past. Okay, we can run it again. Okay, let's run this one. Actually, let me bump it down to 4. Okay, this is, now we should see, okay, that was the fork join really ending. Whoops. Oh, I forgot to put the parameter on there. Okay. 50. Okay. This is a pretty small cutoff. So we expect there to be a lot. Okay. So now there's the work queues were created. Now the question is, will the work queues keep growing or not? It could be that Java allocates work queues big enough at the beginning that they don't have to grow. But I'm almost expecting them to grow. It doesn't look like. Looks like the work queues are big enough. Yeah. So there was the work queues got allocated. Notice that it slowed things down a lot. So the slowness wasn't the size of the work queues didn't grow, but the amount of putting in. So much stuff got put into the work queues, and so much stuff had to be pulled out of the work queues that now our time is not really spent working on our computation. Now we're seeing the overhead of the actual fork join algorithm. The number of tasks is grown so large that we're spending too much of our time forking and joining tasks in the work queues. So there's too much stuff. There's too much stuff in the work queues now. Okay, so somewhere around 15 was a kind of an optimal size. The work queues themselves didn't grow to some massive amount. Okay, so one of the nice things about this Fibonacci example is we could play around with this threshold and tune it. Whereas with this array bound one, there was no way we could tune it with the sequential cutoffs. There was just nothing to tune. Okay, so we've seen a lot now with we've got a better sense of what work join can do, how work join can really scale by doing this kind of, it's a dumb example, Fibonacci, but because it's so CPU bound, you can watch it scale and you can see how the threshold matters. If the threshold gets too small, you're just putting way too much stuff in the work queues. Okay. All right. Okay, we've run out of time. Okay. And like I said before, if you have questions, I'm going to put the video up here. If you have questions, please, send me an email or or I can talk over Zoom. And I'm not sure what we're going to do next. We've pretty much exhausted, unless we come up with a really compelling example of fork join, we're going to try to find another way, another form. There's lots of different parallelisms out there. We've actually gone through like 3 or 4 different kinds of parallelisms so far in this course. We've pretty much gotten a good sense of fork join. I think one thing I'd like to do is parallel streams. I mean, that might be the next thing to try. That's another part of parallelism in the Java language, what are called parallel streams. So we'll see. Maybe we'll try doing parallel streams next. If somebody can come up with a really nice example of fork join. Though we've seen how fork join works. We've pretty much explained fork join. We haven't seen a really great example of using it, but we've seen how it works. So the next thing might be to do parallel streams, because that's another important form of parallelism that the recent versions of Java have, starting with Java 8. Parallel streams started with Java 8. Fork join started with Java 7. Parallel streams were in Java 8. So it's another form of a recent form of parallelism. So I'll see if I can find some nice reading and we can look at some examples of that. Okay. Otherwise, I will, let's see, stop sharing, and I'll end the class. If you have questions, please send me emails or form a chat. Okay. So I'm going to end the meeting now. Bye.
Bye.
Yes, sir.
Bye.
Bye.